Welcome to our presentation on the use of direct reduced iron and hot briquetted iron, that is DRI and HBI, in iron making and steel making. In this study, we will see how DRI HBI can reduce environmental impact and improve efficiency in steel production. Let's dive into the key aspect of this innovative approach. Steel is a cornerstone of industrial progress, valued for its strength and ductility. The industry primarily uses three production routes, and what they are? Primarily, it is blast furnace with the basic oxygen furnace, that is what we are saying BF BOF route. Then electric arc furnace and direct reduction route, that is EAFDRI route. However, traditional methods, especially the blast furnace route, produce significant emissions. DRI and HBI offer a promising solution to reduce environmental impact while maintaining efficiency. Coming to the direct reduced iron or DRI, it is produced by reducing iron ore using natural gas or syngas or hydrogen, while hot briquetted iron or HBI is compacted form of DRI. It is the same DRI, it's compacted, which is designed for easier handling. These materials offer advantages like high bulk density, a consistent composition with minimal harmful elements, excellent conductivity, and low reactivity with water, making them ideal for various steelmaking process. So once again, we can say that the advantages is due to its high bulk density, consistent composition, minimal harmful element, excellent conductivity, low reactivity with water. All these make these hot briquette iron successful item for steel making processes. This slide compares the experimental impact of major steelmaking technologies. The blast furnace would consume the most energy at 22 gigajoule per ton and emit around 2.1 ton of CO2 per ton of steel. In contrast, electric arc furnaces and DRI possess with them while processing far more efficient value compared to blast furnace, and with DRI emitting only zero point 0.4 ton of CO2 per ton and negligible CO emission. So we can say around 2.1 ton of CO2 per ton of steel in blast furnace route if compare with a negligible emission in this DRI EAF route, then DRI EAF route become very much prominent as far CO2 emission is concerned. DRI also uses less water and land, making it a sustainable choice compared to blast furnaces, because in blast furnaces we have route a lot of other units which back up the core blast furnace reactor or SMS converters is required a lot of other units which will back up these core units, and compared to these, DRI uses very less land because it is a smaller unit. In blast furnaces, DRI and HBI are used to produce pig iron. Their inclusion reduces coke consumption, which directly lowers CO2 emission and the energy required for pig iron production. Actually, productivity can increase by up to 10%. For instance, using 200 kg of HBI per ton of hot metal significantly, it is a big value, reduces the coke rate as demonstrated by the data from AK Steel. In basic oxygen furnaces, the metallic charge typically consists of 85% cast iron and 12% scrap, with DRI or HBI added to enhance efficiency. HBI can charge up to 45 ton per hit, reducing the reliance on scrap. With an 80% yield, HBI perform comparably to scrap. It's rather, we can say it's better than scrap, but offer greater consistency. Also, this HBI offers a greater consistency also due to fewer contamination. So we can say that HBI performance is much better than scrap. If we compare both of them due to these properties that which we have just discussed. In electric arc furnaces, DRI and HBI help lower residual metal like copper and tin. For best results, they should be charged in the second bucket within a carburized bath. Their high conductivity ensure fast melting, improving arc stability and metallurgical yield, which is a very important parameter that we have just discussed, that conductivity ensure fast melting. Efficiency depends on DRI quality, temperature, and the furnace's power and thermal efficiency. So we can say that if conductivity ensure fast melting, then definitely thermal efficiency and power consumption, thermal efficiency improve and power consumption go on decreasing. So it will be easier to produce at low cost. Now coming to the laboratory experiment explored how HBI interact with pig iron at temperature from 1200 to 1500 degrees centigrade. At 1200 degrees centigrade, no melting or diffusion occurred, but at higher temperatures, carbon diffusion lowered HBI's melting point, enhancing the metallurgical yield in both basic oxygen and electric arc furnace. Microstructure analysis confirmed these benefits, what we have discussed just now. It also highlighting the role of carbon diffusion. So altogether, all these gives a advantage. The study concludes that DRI and HBI significantly enhance steel making. No doubt about it, as we have discussed all the positive signs and characteristic in earlier slide. In blast furnaces, they reduce coke use, and consequently we can say once coke reduce, there is a drop in CO2 emission too. In basic oxygen and electric arc furnace, proper carburization maximizes yield with DRI HBI ideally charged in second bucket for EAFs. Overall, these materials promote sustainability and operational flexibility across steelmaking process. Thank you.